Hello, I'm David. I'm the coordinator of the Maths Learning Centre. It's semester 2, 2021, and this is a revision seminar for data analytics. Those of you who are watching this after the fact, hello from the past. I hope things are nice there in the future. We're about to start. I've got some requests and I'll see what I can get through. All right. I'm just going to talk about a little bit first about how I think about p-values and confidence intervals and how they're related to each other and what they're designed to do. So I can let my brain sort out some things and also hopefully it'll make the other things I say make sense. Okay, the purpose of statistics is to answer questions while simultaneously coping with variation. We wouldn't need statistics if things were always the same. If all people always reacted exactly the same way, we wouldn't need statistics. And we wouldn't need science either. You just like do it once and then it'd be that way all the time. So we need statistics because things vary. And the way of dealing with variation is to think about probability. The purpose of probability is to say, well, we don't know what the answer is going to be, but we do know it's more likely to be this than this. That's the general idea. The types of questions that you can answer with statistics are only very specific questions. Statistics is not good at answering general vague questions. That's what arts is for. So sociology, where you do complex interviews with people and write down their whole story and go into great detail with that sort of thing. That's designed for vague questions, but statistics can only deal with specific questions. And the two most specific kinds of questions you can ask are what is this number? There is some number that you do not know, and in fact you will never know, and you would like to know what it is. Okay, and the other, I'm going to leave a space, and the other question is that you can ask is a yes or no question. This is the most specific kind of question it is possible to ask, a yes or no question. Is it this or is it not? And a lot of the time, the yes or no question you ask is about a number. So, for example, it might be, so this, e.g., what is the mean weight of cereal in the boxes like this? Damn it. All right, classic quality control question. So it's saying, here's the number, the mean weight of cereal in boxes like this, and we know what it is. But you could also ask a yes or no question about that same number. Is the mean weight of cereal 500 grams, like it says on the box? And that's a yes or no question. Is it 500 grams or is it not? Yeah. The two classic kinds of questions. But the yes or no questions don't have to be about a number. They can also be, is sleep related to exam grades? That's a yes or no question. They're either related or they're not. This is not specific enough for statistics to be able to answer it. You would have to figure out how you're going to measure sleep first, like is it number of hours per day or what? So you need to figure out how to do that. And in this course, most of that's all done for you. Except, did you have a project to do in this one? Yeah, last semester they had a project where they had to actually collect data and do stuff to it. So, which is, yeah. So there you go. Every semester this course is different. So yes or no questions can be just about relationships, or they can be about numbers. And some yes or no questions about relationships can be pitched as if they're about a number, actually. And that's generally the vibe of statistics, is you want to pitch your question to be about numbers if you can. But what's the number questions are about numbers. Right, cool. P-values are designed to answer yes or no questions. They can only answer yes or no questions, and no other questions can be answered with a p-value other than that. So yes or no questions are designed for p-values to answer, and p-values, it's not like the p-value answers the question, but p-values, you know, in hypothesis testing. Do they call it hypothesis testing in this, or significance testing? Okay. Over in psychology, they call it significance testing. So just, yeah. P-values answer yes or no questions, and that's the only thing they're capable of answering. And the idea is that you choose a cutoff, and if the p-value is lower than that cutoff, then you decide that the answer is one answer, and if it's higher than that cutoff, then the answer is the other answer. Depending on the way you ask your question, it's either the yes or the no. You usually try and pitch it so that the answer is no when the p-value is low, but it depends how you ask the question, because you can always ask a question the other way around. I'll talk about that a bit more in a second. And then what's this number question is usually answered with a confidence interval, because you know that you'll never actually know exactly what the mean is, because you only ever know what the mean is from your data. You never know what the theoretical mean for all possible serial boxes that could exist is. And so that's what confidence intervals are for. Your lecturer talks about interval estimates and point estimates. They're both trying to answer the question of what's this number. But from a statistical point of view, a point estimate is all well and good, but you know that one number is not the right number. So you want to do a range of possibilities. So this process is called estimating. If you do any later statistics courses in this degree, they will have like half the course on figuring out what the best kind of point estimates are and why they are better than other ones. So yeah, there you go. Econometrics 2 is pretty much all regression, but there's another, yeah, anyway. And you can talk to Miscellaneous Center about second year courses too, just so you know when you get there. Okay, so that's those things. So I find it useful to know that if I'm supposed to be doing a hypothesis test, that I need to go looking for the yes or no question, and then I can figure out what the things is. So I'm going to focus on this for a moment. Right, one more thing to say. These two are connected to each other, and I've tried to make that clear already, that is the mean weight equal to 500 is related to what is the mean weight. And so a confidence interval is all the numbers for which is the mean weight equal to that number, you think it's reasonable to say yes. So they tend to match together. Okay. So I need to do it as an example probably, just to make sure we've got the right idea here. No, just a little more philosophy. The way that statistics works is that you're trying to imagine all the situations that could have happened. So what you do is, if you've got a question like, is the mean weight equal to 500? You would get a whole lot of serial boxes, which I'm going to draw as rectangles, and you would measure all their weights. That's a hash symbol for a number, by the way. Okay, and then you would ask yourself, and you would think there's two options for what could happen. It could be 500 or it could be not 500. Or you could run your options differently. You might be only really care if it's less than 500, because if it's more than 500, cool, my customers have the amount that you've said they have. And so your question is not now, is the mean weight 500, but is the mean weight at least 500 or less than 500? So you've got to choose, and the text of the question should make that possible to figure out. If not clear, it's often a little bit ambiguous, and that if your lecturer has written their exam questions well, it should be clear whether they want it to be one way or the other. But no matter how clear you write it, it's still possible to misinterpret. So use some of your ideas of what seems reasonable. But in general, if they say, is it equal, then it's either equal or it's not. So I'm going to do that one. Is the mean equal to 500 grams? All right. And that mean we're talking about is the mean of all possible cereal boxes that could possibly be produced. So when we talk about a population in statistics, you feel like when you're talking about people, a population is, you know, they exist somewhere and you've just got some of them, but the population of cereal boxes doesn't even exist yet because a lot of them haven't been made. The thing about the cereal boxes that my machines on my factory and my factory workers can produce. So yeah, so is the mean equal to 500? And there are two answers to that. It either is 500 or it's not. And the one that you choose to be the null hypothesis is the one that goes with being a single number. So the null hypothesis is that the mean is 500. And the alternative hypothesis is that the mean is not 500. The reason why I say that, this one is not the null hypothesis because there are many ways to not be 500. And I'm going to have to do calculations with numbers in them, and I can't use all the numbers that aren't 500 in my calculations because there's infinitely many of them. My calculations have to be based on a single number, and so my null hypothesis has to go with being a single number. So it doesn't always go with no, it just goes with whichever one is a single number. Yeah, whichever one only has one way to be, that's the null hypothesis. All right. And then I would ask myself, if I really did live in the land where the mean really was 500, and I collected data like the data I've collected, how surprised would I be if I got this data? That's what I'm asking myself. That p-value is a level of unsurprise. It's your level of comfortableness with this data. So the lower that p-value is, the less comfortable you are with that data appearing under this assumption. It's a big double negative, like it's not 500. So yeah, so that's too hard with this. And so what we want to do is we want to calculate a single number from my data that I can use to make my decision of how uncomfortable I should be with the data that I've got. So I need to get all this data and calculate a single number. And the philosophy of statistics is that anytime any data is collected of any kind, anytime any number is figured out of any kind, it can be measured, it can be done with dice, it can be calculated from a group. Any number has somewhere in the background of the universe a list of all the possibilities that it could have been and how likely they all are. So in my head, there's a big angel somewhere with a great big book. And so anytime you measure stuff, you go, oh, right. And the answer is 4.7 today. That's just how it's done, right? And so somewhere there is a list of all the possibilities and how likely they are. Now, since we have not met the keeper of the distributions, we don't know. And I've used a word there. The distribution is the name for the list of all the options and how likely they are. That's what we mean by distribution. It comes from the English word distribution, which means how things are spread out. You talk about the distribution of a newspaper, which is where the newspaper goes. That single number has a list somewhere of the probabilities that go with it. And I would like to know how likely is it to get this single number if this is really true. But the only way to do that is to know what the distribution is. And most things, we have not the slightest clue what they are. And some very clever and hardworking people, mostly between 1890 and 1930, created some cool calculations that they knew what the distribution was going to be. And so we've discovered that if you do this calculation, like that, that's the sample mean, That's the sample standard deviation. That's the number of serial boxes I've got. That's the number from my null hypothesis. If I do this calculation, then I am able to know that the correct distribution is the n-1th t distribution. If I had done a different calculation, it would have been a different distribution, but I wouldn't have known what it was. And Gossett, working at Guinness in about 1910, made up a good old table for the t distribution and was able to figure this out. So that was great. Very happy with Gossett. He published his results under the name Student because all of his research belonged to Guinness, and he wanted other people to do it, so he put it under a different name, which is why it's called the Student's t distribution if you Google online. But honestly, it doesn't really matter. All that matters is that if you do the right calculation, it's possible to know what distribution it comes from. And so you say, well, these are all the things that the t could have been if I'd collected different data in the land where this is true. These are all the things that the t could have been, and this is how likely they all are, and this is my value of t. And it's really quite far out relative to all the others, because the most likely thing to happen would be to get 0, and it's really quite far away from 0. So maybe I don't believe that mu is 500 after all, and it's probably something else. That's the not correct way of saying it, but that's the idea. How do people feel about that vibe? Cool. So the big problem in statistics is, what is the correct thing to calculate so that you know what the distribution is? And luckily, some people have solved that problem for us. And there are about, what, 16, I think, in this course, if you count the one side, the knowing standard deviations and not knowing standard deviations, and 2 groups and 1 group. And did you do the chi-squared test? Oh, really? It's so sad. Best. I mean, it's really hard, but it's to do by hand. That's why I have computers. But it's you didn't do the chi-squared test? What's the world coming to? Anyway, sorry. Okay, so there's all these different situations. Is that a cheat sheet you've made for yourself? Sorry? Is that a list of them? Oh no, it's a cheat sheet. Yeah, can I look? Do you get to have one of these in your exam? Yeah, we think either it's a formula sheet or a cheat sheet, but it doesn't specify which one. So are we allowed to put examples? You would have to ask your lecturer. We have. And what has your lecturer? Yeah, the reply I got asked last Thursday. Does she only have 1 hour of office hours? I think so. My understanding of cheat sheets is that you're allowed to have whatever you want on them. Yeah, but there's a dispute as to whether it's a cheat sheet or a formula sheet. He said in a lecture at some discussion that it's a cheat sheet, but then he said, oh no, I accidentally submitted formula sheet to the exam. And then I don't know. And we've seen clarification for what's allowed to become a spots. So I would recommend going to someone contacting the head of school or the director of teaching to get them to poke Virginia and say, what's, please answer your emails. I'm sorry, I don't have an answer for that. Yeah, we've also verified that we meant to decide. Oh no, she did it, then she decided she didn't want to do that. And then she didn't do it. So now it's up to us. And she said, okay, you guys can do it now. It's one. Yeah, we're going to hold this onto this. Yeah. Please remember to get it back. Okay, so one of the problems with choosing which calculation you're supposed to do and whether you're choosing the null hypothesis and the alternative hypothesis is that someone asking that question means that you can't tell the difference between the situations. So if you don't know what to choose, then you don't know, then these situations look too similar to you to be able to tell. It's like being able to tell apart people who look very similar to you, like twins who've been introduced to you at, I'm a twin, and we're always introduced that this is Paul and David, but they never say which one is which. They just tell us both names. And so, yeah, anyway. We don't even look the same, but people still just say, these are Paul and David. They don't say, this is Paul and this is David. But telling things apart usually means you have to be able to tell the difference between them. And so you need to know how hypothesis test situations can be different and similar to each other so that you can tell the difference. So, all right. All right. So we have situations where, let me think about this. I'm just wondering about the wisdom of telling you something that I tell the med students, but it would require a change to the way you think about it. So I'm just, no, I am going to run with this. Okay, so there are two main types of hypothesis test situations that go with the two main types of questions. One is about what is about a number, and one is about, is there a relationship? Okay, so if you look at the situation that's described in your problem, it might say, does, does putting the milk in before you put the tea in or putting the milk in after you put the tea in affect the taste, for example? Or does it affect the temperature differently, for example? Or from if I'm going to do an economics or marketing sort of thing, then you could say, does including a diverse array of people, diverse group of people in your advertising produce better sales than all white people, for example? So I would like it to be the first one, but the world is probably not like that, unfortunately, which makes me sad. So those are the sorts of questions that you can ask, these yes or no questions about the relationships between things. Or you can ask yes or no questions about a single number. They're the two main varieties. And the single number questions single number yes or no questions or relationship questions, they're split. And our single number questions can be either about, technically, if you think about the individual objects that you've recorded information about, and I'm going to say they're people, you can record a number for every individual. Now, it might not be people, it might be months, it might be days, it might be companies, it might be petri dishes, it might be computer programs, or if you look in your Excel sheet and you go, these numbers, who do they belong to? They could be people or lots of things, but each of them has a number, or it could be that each of them has a word, a category. All right. So if you're going to ask people a yes or no question, do you agree with bleh? And you say, do people in this area tend to agree more than the people in this area? That would be a relationship question. But the outcome for each individual isn't a number, it's just a word. So if you're going to summarize numbers, then when there's a lot of people with numbers, then you'd summarize that with a mean. You'd average those numbers, and that's what you do. But if everybody has a particular category, these say yes, these ones say no, these ones say yes, these ones say no, then the only way you can't average a whole lot of yeses and nos. All you can do is write down how many of each there is. And you'd normally say like a percentage. And in statistics, they normally call it a proportion. Does that word sound familiar? Proportion? Good, just checking because different terminology. So they're the two main situations. So when you look at the story of what's going on, you think, okay, this story, is it about writing a number down about all the individuals or writing down a category about each of the individuals? And has it been summarized with a mean? Because that means it belongs with numbers. Has it been summarized with a percentage? That means it's really categories. And those are two different situations, and they will go with different types of data. So if we're in this situation and we've got a question about whether the mean is equal to a specific number, is the mean this number, then your null hypothesis would be that the mean is that number. And the alternative, depending on the story, there's 3 options for what the alternative could be. And you need to have a list of probably keywords, and it breaks my heart to say that. But you have to listen to the story that you're presented with. And if they really talk about caring about whether the number is more or less than something, then you're going to have to do a one-sided. Your lecturer does it like this, don't they? Like if it's a one-sided hypothesis test, they write it this way. All right. Okay. I was taught never to do one-sided hypothesis tests when I learned statistics. It divides the number of possibilities by 3. It's not so many things to do. So now there's more situations, because what we're going to the calculation we do is a probability thing. We have to know this calculation, what are all the possibilities for what it could be, and how likely are they all? And how likely they are will be dependent on how much knowledge I have about what's going on. So if I know what the population standard deviation is way back here, where this group was taken from, then that will change the probabilities that come about when I do my calculation. And so that is going to make a difference to what the p-value works out to be in the end. So if I know the standard deviation, then I will do z equals x bar minus the null hypothesis mean divided by the standard deviation. I know what it is on root n. And that would come from a standard normal distribution. But if I don't know, then that will be a t, and I'll use the sample standard deviation. So before Gossett invented the t-test, everyone did this. And then Gossett went, just a second, if I'm using the sample standard deviation, the probabilities are actually different. And he figured out what the correct probabilities were. And this comes from a t distribution with n-1 degrees of freedom. Now, it's not to say that the only way to produce a t distribution is this calculation. The t distribution just lives in, in the Keeper of Distributions great big distribution book. And there are lots of calculations that are capable of producing a t distribution. And there are lots of different t distributions. And they all have a number to say which one they are, and that number is called the degrees of freedom for reasons that are difficult to explain. So I imagine them as living in a great big apartment block, and there's one on each floor, and you go into the lift and you press number 5 and you go to T5. And the Z distribution is the infinitieth floor. This is T infinity. So is there a T table in this course that you have to look up to? Okay, cool. Okay, okay, that's fine. So that's great. And that's pretty much the deal with that, as far as I know. If I'm in this situation, so that's good. So this single number has means or proportions, and it has, do I know the standard deviation? And I end up with these things. And then within that, there's also 3 possibilities for what the alternative hypothesis could be. And which of these alternatives will change the way that I respond to seeing this diagram? If my t is here, if it's a straight up not equal to, then I'll be using both ends to calculate my p-value. And that p-value really is a probability. It's how likely is it to get my t or further out if the null hypothesis number really is the number I hope it is, or hope it isn't, depending on my goal. Yeah, so this would go with an alternative that has a not equal to, whereas an alternative that has a greater than, you would only be looking at this side. And an alternative that has a less than, you'd be looking at this side. We'll stop there for a moment. I think that at this stage, people should have either a comment or a question to make. So could someone please say something? It only has to be vaguely related to this. I wish I had more examples to go with the how do you tell if you're doing a left tail or right tail. It's to do with if it's in an exam situation, then it's to do with the way that the text talks about the goal. So the text could talk about the goal as saying, the factory manager is interested in knowing whether the mean weight of the cereals is less than what the box describes. And so you go, okay, it doesn't really care if it's more than, so I'm going to have my alternative hypothesis as less than. And that's all I could say. I find it really hard to be sure what they want. Yeah, I do know that if they don't specify any words that talk about more or less, then it's just an equal to or not equal to, like it's a two-sided one. And that's the safest one to run with if you can't choose. Yeah, if it was a written exam, you would get marks for at least doing something, but a multiple choice is going to be tough. Yeah. So, yep. I'm hoping that your lecturer writes the questions in such a way that both options are not options on the multiple choice. It'd be really distressing if one of the p-values was half the other one, and then you go, oh crap, now she wants me to be able to decide if it's one-sided or two-sided. But if she's writing it well, she'll only assess that a couple of times. Yeah, anyway, I can't give you anything more than that, I'm sorry. But if you have lots of examples of practice ones, then we can try and categorize them at least. Okay, so that's that story. If we're looking at yes or no's, so for example, we are wondering if, what percentage of children finish all their homework, and is it more than half of them? That would be a hypothesis test concerning this number, which I don't know. And it's traditional to call this proportion that you don't know P. It's traditional to call the mean you don't know the Greek letter mu. You did do things with like P hats and stuff, didn't you? Yeah, okay. And, is the proportion equal to this number? And then your null hypothesis would be that the proportion is the number. And it's traditionally called P naught because it's the proportion that goes with the null hypothesis. And that question that I asked of like, what's the proportion of kids that finish all their homework? And is it more than half? I would do that as a null hypothesis with a greater than. Is the P more than half? Yeah. So there is no standard deviation to know in this situation. That it's not a standard deviation sort of situation because the original data doesn't go with standard deviations. It just goes with yeses and nos, and it's just a percentage for one and a percentage for the other. So the percentage for one is called P and the percentage for the other is called Q. Those are the numbers that end up in the story that you're looking at. So P for yes and Q for no. Just be careful, you might be interested in the ones that say no, in which case that one's going to be P. P is the one that you're interested in and Q is the other one. Like P is the one I'm interested in, this is the rest. So if you think that 50% is what you're aiming for, well, this would be also 50%. If it's 20%, this would be 80%, and that add up to 100%. So is the proportion equal to a number? Then we've discovered that what we calculate is this P hat, I believe is a traditional thing that you write, which is the one that you get from your sample, minus the P naught that you're thinking of, and the square root of P naught Q naught on N, I believe. Am I right about that? I'm sure I saw it. Oh, okay. Let me just pause for a second. All right, just let me stop on my story of which hypothesis test goes with what and talk about sampling distributions. So, you know how I said there's the keeper of the distributions? Well, you need to, the only way to figure out the p-value is to know the probabilities of everything, which means you need to know when you do a calculation on data what the distribution is. And so if you have individuals that all say a yes or no, and there's n of them.
What?
If you dare.
Sorry about this.
Okay, so camera fixed. And you have n of them. And then what you write down is like the number of yeses is like x. Then the p hat is x on n. Okay, but completely regardless of this p hat thing, and the true proportion of yeses is p among the collection of all possible people that I could have collected. So not just these people, but everybody, that proportion is p. Then each individual person is called a Bernoulli trial. So when you take from, when you do an experiment that has a certain probability of coming up yes, and you write down whether it's yes or no, that single person or dice roll or whatever it is called a Bernoulli trial. I mean, it's only called a Bernoulli trial if each individual is independent of every other individual, and if the probability of getting a yes, I think they call it a success, is the same every time, and there's 3 rules. What's the other one? Oh, and there's only 2 options, yes or no. Okay, right. And when you do several Bernoulli trials and you add up how many times you get a yes, then that X has a probability as well. So this is the story. I'm just going to draw a new picture. For a person, they're either yes or they're no, and this probability is P, and this probability is Q. And that's a probability distribution as well. It has like yes and no, it has this probability and this probability. But when you have a collection of individuals, and they're all saying yes and no, and you count the number of yeses, and if these are all this person, right, but over and over, like this story over and over again, then X could have anything up from, could have nobody say yes, 1 person say yes, 2 people say yes, all the way up to everybody saying yes. And each of those has a probability of their own. And the formula for that probability is the binomial distribution formula for the probability. Did you get that formula in your course?
Yeah.
Seems like something that Virginia would do.
Yes.
Yeah, it's got like power p to the power of x and that sort of thing. Like n choose. No, cool. No, just saying that's not in your course. Awesome. That's fine. The name for the distribution of probabilities here, sorry, is a binomial distribution. Yep. P and Q. P is the probability of getting a yes, and Q is the probability of getting a no. Where yes is whichever thing you're hoping to count, which could be a bad thing. dying here.